Now we'll turn to dot product over GF2. So here's a couple of GF2 vectors, and we're taking the dot product in the usual way. We line them up, multiply corresponding entries, and then add the result. The difference is that we're adding using GF2. So 1 plus 0 plus 1 plus 0 plus 1 ends up being 1. Let me give you an application of this of dot product over GF2. A usual way of logging into a computer is by sending the password over the wire to the computer. The computer checks to see if the password matches its records and lets you in if it does. Now, that's dangerous, because if an eavesdropper managed to see the password going over the wire, she could then break into the computer herself. So here's an alternative approach. It's called challenge response. The computer asks you a question, and you give the answer based on your knowledge of the password. You do this a few times until the computer is convinced, yeah, this human knows the password, better let him in. This is potentially safer against an eavesdropper because the password is never sent over the wire. So here's a simple authentication scheme, not one that's really secure, but one that illustrates the idea of dot product over GF2. So the password is some long n vector over GF2, we'll call x. And the question is another n vector, which we'll call a. And the human sends back one bit, namely the dot product of the question a with the password x. So here's an example. Let's say the password is 10111. Okay, obviously this is too short to be secure, but it's good for illustration. Maybe the computer chooses as its question the vector 01011. It sends that to the human. The human computes the dot product of that question with the password and ends up with 0 and sends back 0 as the response to this question. Let's call that response beta 1. This is repeated several times. Now, how can an eavesdropper cheat? Well, let's say she observes a sequence of challenges, A1, A2, A3, and so on, and she observes the human's corresponding responses, beta 1, beta 2, and so on. Can she use these to find the password? Well, she knows that the password must satisfy these equations. So if she can solve this set of equations, can she find the password? Well, there are two questions. Maybe this set of equations isn't enough to precisely pin down the true password. So how many solutions are there to this system of linear equations? And how could you even compute them? So we'll study these questions later. And what's another way to cheat? There might be a way that Eve, even if she doesn't know the password, can figure out the answer to a challenge. So in order to explore that, we have to introduce a couple of algebraic properties of the dot product. So commutativity, homogeneity, and the distributive law. So let's say Eve observes two challenges, 01011 and 11110, and the responses that the human gives for those challenges. Here's how she can figure out the response for a challenge she hasn't yet seen. The dot product of the sum of these two vectors with x is equal to the sum of the dot products using the distributive law. She knows the dot products for each of these two. She can add them up to get the response for the sum. So for the challenge that's the sum of these two vectors, she can compute the right response. More generally, suppose some vector, unknown vector, satisfies a bunch of equations. Are there other equations that it also satisfies? The answer will have to wait.